Good morning, everyone. I'm very glad that you registered for this introductory course, the Deep Learning with Keras. My name is Jessie. I hope that after these 2 hours, you will have an idea of what deep learning is and how to use Keras to build a deep learning model. Okay, let's start the course. These days, when we read the news, we hear a lot about the artificial intelligence, machine learning, and deep learning. These three terms that we often use is interchangeable. But what actually are they? And what are their relationships? Here is a diagram which apparently shows their relation. The artificial intelligence is a very broad conception. If a machine shows cognitive capacities, then we can call it artificial intelligence. So it may include reinforcement learning, computer vision, speech recognition, knowledge inference, and so on. In other words, artificial intelligence is future, and it means the human intelligence is exhibited by the machine. The machine learning is a sub-branch of artificial intelligence, which focuses on creating algorithms that learn from the history data and make predictions for new data. Therefore, machine learning can be regarded as an approach to achieve the artificial intelligence. Also, deep learning is a technique for implementing the machine learning. It also creates algorithms to fit in the training data. However, it specifically uses an artificial neural network, which is inspired by the structure of neurons located in the human brain. In this 2 hours course, we will cover 4 parts. The first is the deep learning foundations. The second is Keras installation and its API. In the third part, we will introduce a simple Keras example on the handwritten digital recognition problem. And in part 4, we will talk about how to improve the model that we built in part 3. Okay, let's begin with part 1, the deep learning foundations. Deep learning, also called the deep neural network, is a learning paradigm that uses an artificial neural network as a learning model to fit the history data. In an artificial neural network, as shown in this picture, there are 3 kinds of layers: the input layer, hidden layer, and the output layer. For each of these yellow round dot, we can call it units or perceptron or a neuron. The unit numbers in the input layer indicates the shape of the input. Here we have the input of shape 3. For the units in the hidden layer, we can simplify to call it hidden units. This is a hyperparameter for this hidden layer. You can define this number as 3 or 4, or maybe for a large network of 112. Okay, similar to the input layer, the units in the output layer indicates the output shape. For example, an image classification problem to classify between cat and dog. The input layer represents each pixels in an image, while the output will be the categories. Like within this image, whether it refers to a cat or a dog, or some other categories like pigs. Another example is a house pricing prediction model. The input will be the feature regarding a house, like how many bedrooms are in this house and where is this house located, its postcode, also when did this house been built, and the output will be the history trade prices. So here there will be only one output, and this is a regression model. The following, we will talk about foundations in the neural network. The first is the perceptron. This is also called as a neuron units. And then we will talk about activation function. After, we will introduce the forward and backward propagation algorithm. And then we will talk about the batch size and the optimizer that are used in the deep learning. First, the perceptron. A perceptron is a neural network unit. You can also call it artificial neural. In the left figure, as we can see, the units in the hidden layer and the output layer. So for each of these units, we can have its internal view as shown in the right figure. Each neuron can be divided into two parts. The first is a weighted sum. As we can see from the left one, each neuron is connected to all its input. Also, we will have a weight for each input, indicate the relevance of each input to these units. The reason for the weights is that, for example, in the house pricing prediction problem, if the first input is the number of bedrooms and the second input. Also, here is the internal view of each yellow dot. As we can see, the first part is the weighted sum. Each neuron is connected to all its input, and we have a weight here for each input, indicate the relevance of each input to these units. The reason is that, for example, the house predicting problem, if the first input indicates the number of bedrooms and the second input indicates whether this house has air conditioner or not, we can assume that the weighting connects to the number of rooms will have higher weights than the other trivial features. So that's why we will have the weighted sum here. Mathematically, it is presented right, and they is equal to the weight multiply x, the input x, plus bias. Where W is the weight for the input layer and B is called the bias. By using the data to train this network, which means that we have the supervised inputs and labeled outputs, we can then learn the weight and W for this, weight W and bias B for this architecture. For this first part of the neuron, it is actually a linear function. We have the weights as multiple inputs and a bias. The second part of the section is called an activation function. The purpose of the activation function is to add some kind of nonlinear property to the function, which is the core of the neural network. Without the activation function, the neural network could perform only linear mapping from the input x to the hidden units, and then also linear mapping from the hidden units to the output. So when we are trying to learn something from more complex mappings, the linear network without any activation function would not be able to realize such complex mapping mathematically. Therefore, it cannot solve practical tasks. Here we have a simple activation function G. If the input, the weighted summation of the previous layer is bigger than 0, then G is equal to 1. Otherwise, the output of the activation function will be 0. So this simple activation function G here can express classification answer, like yes is for 1 and no as 0. One important thing here to understand is how to update the weight and the biases from the history data. Consider this single neural network. Ideally, we would provide a set of training examples and its ground truth, and we adjust the weights and the bias of the network to fit into the data and minimize the predicted error at the output. Therefore, with optimization, some optimization algorithms, the weights and the bias are changed little by little. This is called the progressive learning. However, now for the G activation function we talked before, it has a big jump in the activation function of the neurons here. So we cannot do the differential or derivation in math, as we cannot progressively learn the weights and biases. So right now we may need a continuous activation function that can progressively change from 0 to 1 with no discontinuities. Let's look into the next part. Here is a commonly used activation function called the sigmoid. Its presentation can be seen from the graph, and the mathematical formula is presented as 1 divided by 1 plus the exponential negative input d. The unit with the sigmoid activation function will have the same behavior as our previous perception, because it also will activate the outputs to 0 and 1. So it can also answer a maybe question whether it is 1 or 0. But it is better than the previous perception activation function, since this change is gradual, not a big jump, and indicates that it can be differentiated. The sigmoid is not the only kind of this smooth activation function used for neural networks. Tangent edge is also a sigmoid-like function. Look at this figure. The green line indicates the tangent edge, and the red line indicates the sigmoid. They are of the same sigmoid shape, but tangent edge is better at the range of. It is ranging from -1 to 1. However, the sigmoid is only from 0 to 1. So the advantage is that the negative inputs will be mapping strongly negative, and the gradient of tangent edge is stronger than the sigmoid. So the derivatives are steeper in the tangent edge. Rectified linear unit ReLU is also a very popular activation function for its good experimental results, and it's very simple. just as the max of 0 and the input d. The graph is shown here. As you can see, the function is 0 for all the negative values, and it will grow linearly for positive values. One problem we see in the ReLU is that the ReLU units remains inactive if the input is negative. That is, the output is same for the input negative 1 or input negative 3, which means that once the neuron or units goes into the negative states, it may stop changing, responding to the changes in the input or errors, because the gradient here is 0. So this is called the dying ReLU problem. We can correct this by making use of a revised ReLU, by simply making the horizon line into non-horizontal components. This is called leaky ReLU. From the figure, we can see when the input D is negative, we will have activation equal to the maximized 0.01 input. Since the ReLU and the leaky ReLU is less computational expensive than the tangent edge and the sigmoid, it is more simple in the mathematical way. So it is a good point to consider these two activation functions when we are designing deep and complex neural networks. Softmax is another activation function that I would like to introduce here. It is unlike the previous ones. It not only maps a single output to the 0 to 1 range, but also maps maybe multiple outputs in such a way so that the total sum of these outputs is 1. Here listed the mathematical distribution for the softmax activation functions output. For example, the image classification problem. We have an image to classify whether it is a cat or a dog. This is a multi-classification problem. In this concrete example, we assume we got the probability for the first neuron is 0.7, which indicates for the cat, and the probability value for the second unit is 0.2, which represents for the dog, and maybe for the third neuron is 0.1. So by apparently, we will pick the largest probability of the outputs as the result. Therefore, we can infer the input image is a cat. This is how softmax works. The softmax activation function makes the summation of the output along all its channels or neurons are equal to 1, because these are represented as the probabilities. If we dive deep into the mathematical equation, we can find that the softmax activation function is actually a generalization of the sigmoid function. That is, if k is equal to 2, only a binary classification problem, then the softmax activation function can be simplified as a sigmoid function. For this concrete example here, if we need to decide whether the input image is a cat or not, in this illustration network, the output layer only has one neuron, and this sigmoid is used to, this neuron will be using sigmoid function to activate the output. If the output is 1, which means that the input image is cat, otherwise output 0, we decided that it is not a cat. So in practical, sigmoid function can only be used for a binary classification, while the softmax is used for multiple classification model. Here we have the summary for the activation functions and their derivatives. The notation they represents the linear summation from the previous input layer, and which is equal to Wx plus the bias. And A is output after the activation function. It doesn't matter that if you are not familiar with these mathematical formulas and their derivatives. In the following, we will talk about how to use the keras to interpret these formulas. Oh, okay, sorry. Okay, now we will talk about the forward and the backward propagation. The deep learning neural network will learn from the training data through a process of forward and backward propagation, and then optimization algorithms can be described as a way to quickly correcting its mistakes. As soon as they are detected, we can see how it works. Diagrams shows a 3-layer neural network. Usually we don't count the input layer. So 2 hidden layers and plus 1 output layer. To make it more clearly, we also add the notations of the weights per meter between 2 layers. And we explicit the internal mechanism of a hidden units, which is 2 parts: a linear weighted summation and then a followed up activation function. The activation function for both the hidden layers and output layers, G here, can be the sigmoid, tangential ReLU, or the leaky ReLU, as we talked about before. Also, if this network is to solve multi-classification problems, we may have multiple outputs, and it can use the softmax activation function also. In this 2 hours course, we were only focusing on the fully connected connections, that is a dense connection. When we build a Keras model, we will first predefine the architecture of a network, like how many layers in this network, and for each layer, how many units will be used, and how the networks are connected. Right now, we only use the fully connected ones, and also what activation functions are using. After that, after we preset the architecture of the network, then we will use this network to fit into our history data or training data, and then find the best unknown weights and biases. Once the model is trained, we will have a pair of the weights and biases. And when new data comes, we can calculate it forward and got the predicted output. Also, at initial, all the weights W1, W2, W3, and the biases, we will have some random initial assignments. Here is the mathematical expression for the forward propagation. For the first layer of the hidden units, there are two parts. One is the dot production between the input vector and the weight matrix W. And then we add a bias parameter. We equal to then follow up, we will have an activation function G here. So the output for the first layer will be A equal to the G1 of the 1. Similarly, we have the same mathematical calculation for layer 2 and the output layer. It is okay that you find these mathematics are too dry and too technical. Here we will talk about how to build it in the Keras. Keras is a Python library that is specifically for the matrix processing in the deep learning. The previous boring and 6 formulas, we can use 5 sentences here to interpret. First, here are the library importation. So we will look into it later. Here, the first line, we will have an input layer and indicate its shape is 3. And in the second line, we will define a dense layer since it is dense connected and fully connected. Also, the units in the second hidden layer is 4. So 4 is written here, and we may using the activation function ReLU. By passing the output from the previous layer X, we can get the output A1 for this hidden layer. Similarly, we will have the same Keras lines for the hidden layer 2. And in the end, it is also connected, and we only have the output dimension as 1. And therefore, we have the first line, the dense layer with output dimension 1, and the activation function is equal to sigmoid, and its input is the output of the hidden layer 2. Then we build the model by indicates the input X and the output Y. After the forward propagation, we can have estimated output. Since we will know the true observation values in the training data, therefore we can calculate the error between the predicted prediction and the ground truth. There are several ways to define the error, or you can say to define the loss. One simple way is the squared error loss. That is, we calculated the mean square error between the predicted output and the ground truth. The other is called the logistic loss, which we will use more often. Still, these equations we don't need to remember. The second parameters in the backpropagation is the optimizer algorithm. It is used for backtracing to propagate the errors through the network, and this process is called the optimization algorithm. Now, if we define the cost function as logist loss, and we decided to use the gradient descent as the optimization algorithm for the backpropagation. Here, the gradient descendant is an algorithm that is used to optimize the parameters, weight, and biases, and minimize the logistic errors between the predicted output and the ground truth. It is an interactive optimization algorithm that can be used in machine learning or deep learning to find the to find the minimum or the optimum value of a curve. The gradient here means the rate of inclination or the declination of a slope, and descendant means the instant of descending. As shown in the photo, maybe at first step we have a very large cost. The vertical indicates the cost, and the horizontal axle indicates the parameter weight that we want to update it. Maybe at the initial we have a very large cost, and during each iteration the weight will update it along the slope or the gradient of this curve, and to make the cost is descending. So therefore, after many iterations, finally we can meet the optimum point, and the gradient descent will be stopped at this lowest point. Also, the complicated formulas is here, how to use the descendant optimization to backpropagate the errors. In contrast, in the Keras, we only need one sentence and we can all do the backpropagation. Still, we need to specify the parameters for the cost function. We have the logistic loss here. Since this is a binary, only one output, so it is a binary classification problem. The logistic loss in the Keras is the binary cross entropy. And for the gradient descent optimization in Keras, it is represented as SGD. S is for stochastic and GD is for gradient descent. The process of the forward and backward of error is repeated several times until the cost function goes below a predefined threshold. So in this way, the parameter is progressively learned and the cost is progressively minimized. In Keras, we will use the function model.fit to do this iterative step, and we will have the training input and output. It is very simple. Pay attention that we have two parameters here. One is the epochs and the other is the batch size. The epoch means that with the whole data set, one epoch means the whole data set is passed forward and backward through the network once. The reason why we use more than one epochs is that since passing the whole data set through a neural network may not enough, we may need to pass the full data set multiple times to the same neural network and updating the parameters like weights and biases. And if pass only once, it may cause underfitting problems and cannot learn the underlying pattern in this training data set. And however, as the number of epochs increases and more numbers of training, the curve may goes from underfitting to the optimum and then to the overfitting. The overfitting means that we learn too much in the training data set and we even learn the noises in this data. And by learning the noises, we may lose the underlying general pattern that we prefer to learn. The other parameter in the fit function is batch bias, batch sizes. Usually, since the whole data may be too big to fit to the computer at once into one epoch, so we may divide it into several small batches. For example, if we have 1 million training data set, we may divide this 1 million data set into 1,000 each batch, and we would have and in this way we would have 100 batches. So the this should be the 10,000. So the 10,000 is called the batch size, and the 100 is called the iterations. The iterations is the number of patches need to complete it in one epochs. In this case, we will take 100 iterations to complete one epoch. As we talked before, the gradient descent is an optimization algorithm used to backpropagate the errors and update the neural network parameters. If we input the whole training data through the network and update the parameters, it will become difficult to train the model quickly because it will cause the calculation very slow. So instead of implementing the gradient descent on the entire training dataset, we can split our training set into smaller sets into each batches and implement gradient descent on each batches one after another. And this is called the mini batch gradient descent. The left figure shows the gradient descent on the whole data set. You can see that the vertical indicates the cost and the horizon x indicates the number of approaches. You can see it is the cost is descending smoothly. In contrast, the mini batch gradient descendant may have a lot of noises in the cost functions. When we do the iterations and epochs, it is still trending downward. The reason for this oscillation noises is that sometimes there may be harder mini batches which may be more hard to train and then cause oscillations to the cost function. So here, the most important thing is to select the batch size. If the size is too large, although it will be smoothly descending, however, it will be very slow. However, if we choose the batch size very small, say 1, then each one example will be a batch, then it will become a stochastic gradient descent. And this oscillation will be at a very large extent and has a very large noises in the cost. Sometimes it won't even converge. In practical, the mini batch sizes should never be too large or too small, but somewhere in between. There are two steps for the mini batch gradient descent. The first is that we need to shuffle the training data sets between the input X and output Y to ensure that the examples will be split randomly into batches so that there won't be any biases in batches. Also, as for the tips for the batch sizes, commonly we will partition the batches as a power of 2, like 64, 128, 256, and so on. It is because that the algorithms will work faster if the batch size matches the design of the computer memory. For the optimizer, except for the gradient descent that we just talked before, there are 3 variants of gradient descent, or you can see the following 3 are also gradient-based optimization algorithms. These 3 variants, the gradient with momentum, RMS prop, and Adam, may include a concept called momentum in addition to the traditional gradient descent. The momentum is used to accelerate the optimization process. Therefore, these three will generate faster convergence and at the cost of more computation resources. All these three optimizers can be used directly in Keras by assigning the optimizer parameter in the compile function to others. Like we can write here optimizer equal to Adam, and then we will use the Adam for the backpropagation optimization. Here is a link for Keras, which listed all the supported optimizers in the Keras. There are others like the ADA delta or ADA grid. You can change the optimizer to any of these available optimizers in the compile function and see how the result is like when you do the application. Also, for your interest, in this slide, we will show what does it mean to have to add the momentum into the traditional gradient descent. On the figure, we have several cost control lines. When we implement the mini batch gradient descent, we can see the oscillation here, and but it also trades towards the optimal value. Therefore, we wish we have faster learning in the trades to the optimal value and less oscillation, less in the oscillation direction. So that's why we want to have a momentum to decrease the up and down oscillation and to increase the trade toward the optimum. Below are the parameter updates mathematical formula for adding the momentum. But in Keras, we only need to update the optimizer parameters here, and all the others will be